Look at this zoom. Disclaimer: never ever try anything you see in this class or any other science class you have at school at home. All right. I had one student one year try to replicate stuff, and the parent called me and was all mad and stuff. So just don't do it. Okay. Secondly, this is the reality of science is that things don't always go as smoothly as you'd like them to go. I thought about this. Well, let me talk to you a little bit about how we used to do this. We used to take a balloon and fill it up with acetylene gas, and then we take that balloon and put it on the end of a meter stick, and we light it with a candle, and you get this little pop, and you get this black cloud that kind of came up, and it really wasn't all that exciting, and there was a lot of uncombusted byproducts and things like that that were just kind of floating around, and it wasn't all that visually stunning or anything like that. So I thought about it last year. I thought we need to revise this so we have more oxygen in with that acetylene gas, because those of you who have seen the spud gun demo, you know that you have the right ratio of oxygen to your propellant, you're going to get a much nicer reaction. Right? Acetylene gas, as you guys will see here. So what I'm going to do is take this calcium carbide and put it in the water, and a reaction is going to occur. But in order to get the oxygen produced, I also need to introduce something called a catalyst to make the reaction of the hydrogen peroxide, or actually have the hydrogen peroxide break down faster. So all this does is it makes the reaction go faster. It doesn't actually involve any sort of chemical reaction with the hydrogen peroxide. So calcium carbide, my catalyst, and I put this in and I cover it up to get the catalyst in there, and I cover up my entire apparatus with this tube to contain the gases. Whoops. Contain my gases. And notice on the top of my tube I have a little plastic wrap. And that plastic wrap serves the purpose of just containing the gases. Now, I would never, ever, ever want to contain those gases so much that I might compromise the structural integrity of my tube and make the tube blow up. So this allows the gases to expand rapidly out the top of the tube. So in our first reaction, we've got calcium carbide, CaC2, and calcium carbide is going to react with water. And the calcium carbide is solid, so we put a little S there to show it's solid. The water is a liquid, so we put a little L there to show it's liquid. And what we produce is C2H2, which is acetylene gas. There's a triple bond between those carbons. We haven't started talking about triple bonds yet, but that's the gas I'm interested in collecting and using for my combustion reaction. Now that's a gas, so I put G there for gas. Now I also get calcium hydroxide, which is aqueous. And you guys in PIB were using aqueous solutions when you were doing that alkali earth metals lab. When you have something dissolved in water, it's an aqueous solution. All right? The second reaction that I'm conducting right now in that tube is a hydrogen peroxide, H2O2, and it decomposes naturally into H2O, this is tube 2, liquid, and O2 gas. Now, we need to get a lot of this O2 gas in a fairly short time frame, so what we do is we use something called a catalyst, once again, to get that reaction to go faster. And so that produces the oxygen gas that we need for the other reaction. Guys, can you come on this side of the barrier? Thank you. All right, so the third reaction, the one that we're really going to be concerned about here, is the C2H2 plus the O2. This is 5, and this is 2. And we get carbon dioxide gas and H2O, which is going to be a gas at this temperature because it's going to be fairly hot. Right now, if you look at this, the stoichiometric coefficients, you see that you've got 7 moles of gas on this side of the reaction, and you've got 6 moles of gas on this side of the reaction. So you're actually having less gas in the end than what you start with. So you might think, well, wait a minute, something's going to happen here where it's going to pull gases into the tube. But what you're not considering is the fact that this also gives up a lot of energy. Right? This reaction actually gets up to about 3,500 degrees Celsius. All right, that's really hot. And because it's so hot, they can use this reaction to cut through really thick metal. If you've ever heard of oxyacetylene torches, if you have metal this thick, you don't want to use saw blades on it because you'll make those saw blades dull in no time at all. So they use these oxyacetylene torches, and it gets so hot they melt that metal as they cut it. So you get about 3,500 degrees Celsius. Now, for those of you who are in physics, you've seen this equation before, right? PV equals nRT when you were in chemistry. Now if I put the P over here and I look at just the volume, my number of moles is going down, but my temperature is going way up, all right? And the fact that the temperature is going way up makes my numerator really big, which makes my volume really big if my pressure remains constant, right? So what I'm doing here is I'm making a lot of volume of gas in a very short time period. So short that it gives us a nice boom. Anytime now! Oh!
Like felt it.
Yeah. Boom.
Echo on the flat irons. That's what I like about that one. Not only do you have a big boom, but the fact that you hear this echo. There's tons of science involved in this process. Tons of science involved in this demonstration. It's something you can't really quantify on a standardized test, so that's something to keep in mind as well. So let's go ahead and head on back in, and thanks for your attention.
Yeah.